Hello guys. In this lecture we want to start another exciting topic of this course called grammars. First let's see why we should learn this and what is our motivation. So far we had two mathematical tools to represent formal languages. First one, sets. We introduced three methods: set builder, roster method, and Venn diagram, and specifically we were interested in set builder. And second one was regular expression or regexes. But what was the problem with these guys? We have learned that sets are not practical and hard to be implemented as a software, and regexes are limited only to regular languages. So these issues raises a need of looking for a new tool that is more powerful and practical and somehow easy to be implemented as a software, and that is grammars. So, roughly speaking, grammar is a mathematical tool to represent formal languages. Even though we can represent regular languages with regexes, but we would like, when we create a new tool, it should have backward compatibility. I mean, this new tool should be able to represent all regular and non-regular languages. You know that we had seen this desire when introducing automata. Of course, our goal is to represent all formal languages, but let's see whether or not grammars has any limitation. Before going further, let's look at our roadmap again and see where we are. As we have learned so far, computer science foundation, that is called theory of computation, is based on these major branches. And we started with formal languages, but it was in fact an introduction, and we said we would get back to this. And actually, we did. First time we introduced regular and non-regular languages, and second time we introduced regular expressions, and this is in fact the third time. So it means that we categorize grammars under the formal languages topic. Let's get started and see what these grammars are. Let's start with the grammars of natural languages because we are so familiar with them since probably elementary or middle schools. Okay, so what would be your reaction if you encounter the following English sentences? Dog, the runs, the runs, dog, runs, dog, the. Yeah, very weird, right? Probably you would say, hey, dude, you need to improve your English language. And you're right, probably. Okay, so what is the problem? All of the words are correct English words, but why these sentences looks so weird? Because the words position have problem. The words position are not as they should be and as they are expected. You see what the problem is? Okay, so we would need a name for this situation. In computer science and linguistic terminology, these sentences are not well formed, or equivalently, they are malformed. Okay, so what? What is our goal here? What are we looking for? Let me start from the end. What does it mean? It means that what is our ultimate goal? Let me first talk about that, and then step by step we will approach this goal. Okay? We are looking for a system or a tool or a software, whatever you call it, that we want to input a sentence And this system is gonna tell us whether this sentence is well formed or malformed. All right, you might ask, okay, so what is the application of this? Yeah, so let me take just one simple and very familiar example. Consider this is a compiler. That's getting very interesting, right? And consider this as your program. So when you write a Java program, it is just a string, a big, very, very big string. And when you feed or input your program to a compiler, the compiler, the first thing that it needs to do is checking the syntaxes and semantics, right? And one important application of this system that I am looking for is whether the program is well formed or it is malformed to give you the warning and the errors. Yeah, just keep in your mind this example, and we might get back to this example later. Okay, so right now we know what we are looking for, but how can we get that kind of system? We need more knowledge to be able to prepare such a system. Okay, so we start from a simple natural language grammar, like the English language that we all are familiar with. After that, we generalize the idea to all formal languages. All right, how can we make a sentence? A sentence is defined as, yeah, we will be using this symbol for is defined as. A sentence is defined as a noun phrase followed by a predicate. This guy is called a production rule because it produces an English sentence. But wait a minute, we have a problem here. What is the problem? Yeah, we said that sentence is defined as noun phrase followed by a predicate. But what are these? Are we familiar with these? Unfortunately, not yet. They are just a variable. This is a variable, this is another variable. So we define sentence, but we introduce two new variables that we need to define them. Okay, so let's keep going. So far we have this, right? And we need to define these variables. We define a noun phrase as an article followed by a noun. That's why we call it noun phrase. And how about the predicate? Predicate, is defined as a verb. Now we introduce three new variables, the article, the noun, and the verbs. So again, let's keep going. So far, we have these production rules. Okay, so how about the article? Yeah, we can define article as an a or the. How about noun? Yeah, just let's define noun as a dog or boy. Yeah, we have millions of other noun, but since this is a simple English grammar, let's stop here to keep it very simple. How about the verb? Let's say runs, walks. Okay, now we have no variables. All of the variables are defined. All right, let's summarize what we got so far. Our simple English grammar is like this. A sentence is defined as a noun phrase followed by a predicate. The noun phrase is defined as an article followed by a noun, and predicate is defined as a verb. And here we just define all of them with the real values. So before going further, let me define and review some of these for more clarification. So we define all of these as the variables we have on the left hand side and on the right hand side. Yeah, we can have some variables like this one. And we have the values or terminals. They can be defined as a value as well. They can be defined as a another variable as well, or a combination of other variables. You see, we have all of these situation, or we can have a mix of both of them. A variable can be defined as another variable followed by a value, or a value followed by another variable, or a mixture of this that we will see in the next slide. And what else? Every grammar has a starting variable, that here our starting variable is sentence. Up to here, we are a little bit familiar with the grammar's terminology, but we still need more knowledge. Now, roughly, we can define a grammar as a set of production rules. Yeah, later, definitely, we will define it formally as usual, but for now, let's say that grammar is nothing except a set of production rules. Okay, so what is the meaning of well formed here? A sentence is called well formed over a grammar. Yeah, they are very important. Over a grammar. So a sentence should be defined as well formed over a given grammar if we can derive it from its production rules. What does it mean? Yeah, I will take a simple example to show you what is the meaning of this definition. Look at this example. Here is our sentence. The dog runs. The question is this sentence a well form over this grammar? Yeah. So the meaning of well form or malform totally depends on the grammar. So always we need to specify the grammar. So let's see whether we can derive this sentence from this grammar or not. If we can derive this sentence, then we would say, yes, this sentence is well formed. Otherwise, it is malformed. All right. So how can we start? We always start from the starting variable. So the starting variable can derive noun phrase followed by a predicate. And both of them are variables. Yeah, we need to derive both of them as well. So the noun phrase will be replaced or will be derived by article followed by a noun based on this production rule. And the predicate will be replaced with the verb by this production rule. Okay? So now we have article, noun, and verb. All right, what is the sentence? The dog runs. So first we need to focus on the. Can we replace this article or can we derive this article with the? Yeah, we need to look for the articles on the left hand side and see whether we have a the or not. Yeah, we see here we have a the. So article can be derived to the. How about non and dog? Now we need to look into the nouns and see whether we can derive the dog or not. Yes, we can do that. So and how about the verb? We are looking for the runs and we see the runs here. So it means that the sentence could be derived by using this grammar. So it means that this sentence is a well-formed sentence over this grammar. I used some words. Let's review them. We derived the sentence from the production rules. So it is well formed. Yeah, this was our conclusion in the previous slide. We used this simple as the derives. So it's a notation for the derivation. Okay, so is this the case that we can have a failure sentence? Definitely. Let me take an failure example as well. The runs dog. Is it a well-formed sentence over this grammar? Yeah, we go over all of those steps. So we have article, noun, verb for the sentence, and yeah, we have this the for the article. How about for the noun? Do we have runs here? When we look into the noun, we cannot find any runs here. So it means that this sentence cannot be derived over this simple English grammar. That's why we say this is a malformed sentence. Okay, so this was just a taste of how a simple English grammar works and how we can derive the English sentences from the English grammar. Now, let me ask another question. Maybe it looks irrelevant now, but yeah, we will see that it is really relevant. My question is, what else we can derive from this grammar? Can I collect all of the sentences that we can get or we can derive from this simple English grammar? Yeah, we can do that. So here I collected all of the sentences that can be derived from this English grammar. A dog runs, a dog walks, and so forth. Yeah, I collected all of them and put them in a set. Okay, now since we are here, let me ask this question. What can I call this set? It is a set of sentences that we can derive from this grammar. In other words, this grammar can produce or generate these sentences. What do you think we can call this set of these sentences? Most likely, most of you guys said the correct answer. Yeah, these set of the strings is in fact the language that can be generated or produced by this grammar. So grammar, in fact, produces or generates sentences. Fantastic. All right. Now let me go over all of the terminologies we introduced so far, and let's summarize them in one slide. So we talked about the production rules, and we used this guy as is defined as symbol, and also we talked about this side of the production rule as the left hand side or LHS, and yeah, definitely the other side as a right hand side, right? And also we introduce a starting variable. Every grammar has a starting variable, and also regular variables. And also we talked about these values as the terminal. So these are all of the terms that we use in the previous slides. Okay, now it's time to generalize the idea that we just learned to formal grammars. What does it mean? Yeah, let's see. So let me explain first by a simple formal grammar. Look at this grammar. Yeah, instead of the sentence or those words that had some meaning, now we have a grammar which looks like a mathematical tool right now. Okay, so this is just an example of a formal grammar. Now, let me talk in detail about its ingredients. So the variables we use the capital letters like this S, this B, you see. The starting variable always is S unless we specify something else. The terminals are being represented by lowercase symbols like this A and this B, and also this lambda that is our familiar empty string. Okay, so we can have the terminals alone here or a combination. So we can have a string as a terminal. And also we have another term here that we call them sentential form. Sentential form is something like this, a combination of a variable and terminals, or like this. All right, now let me take an example. So here is the grammar. S is defined as A, S, B, and S is defined as lambda. The question is, how can we derive this string? Oh, you remember that string and sentence is exchangeably be used, but when we are talking about the formal grammar, we usually use the string. All right. How can we derive this? We always start from the starting variable. But if I start with this one, it is already, derives the lambda, so I cannot go further. So definitely, I would need to start with this. I would say S derives A S B. Okay, so this S, which is a variable, can be derived or substitute with something else. Okay, so this is a recursive operation. I keep an eye here that what string I am looking for. So I am looking for AB. Okay, so I can substitute this S with another ASB that would be A, ASB, B, yeah, or I can substitute it with lambda by using this production rule. Which one do you think that leads to this AB? Absolutely this one, right? So because this one is increasing the number of A's on the left side and number of B on the right side. Okay, so if this is the case, then I would say A, lambda, and B, and we know that lambda is an empty string and it's a neutral thing for the concatenation. So this guy is equivalent to AB. All right, to specify that how we derive this AB from this grammar, it's a good idea to, at the beginning especially, we would say, okay, so we use production rule number one here, and then here we use production rule number two. And this is just the equivalency between the strings. Okay, so this is the way that how we derives a string from a grammar. Yeah, here I ask, could we derive this string if we had started with rule number two? Yeah, already responded to this. So S derives lambda, and then we are all already done. So we cannot go further. Definitely, we would need to use this for the beginning. Let me take another example. How about AABB? The same grammar. Okay, now we are a little bit more knowledgeable. We would say, okay, we start with this. We use the production rule number one, and we have A, S, B. We keep an eye here that we are looking for two A's. So we substitute this S with another ASB. So as I said, this is a recursion, and we can use whichever that works for us, this S or this S. So this derives by using the production rule 1 again. It will be A, S, B, B. So in fact, this is the old s here, right? Okay, so we keep an eye on our goal is AABB, and we already have AABB. So we substitute this S with the second guy, lambda, and we are done. It will be AABB. So we used here the second guy. You see how we derive a string from a given grammar? All right. We have a convention to make the grammar a little bit more compact. So if we have on the left hand side the same thing, we can combine these two in one row. How can we do that? Yeah, we just use a vertical bar like this, and we would say S is defined as A, S, B, or lambda. So in this way, we can combine two rows into one row. One more time, there is an or. This means or here. And here I put an explanation here for your reference. Now let's sharpen our knowledge and skill by practicing on how a grammar produces a language. So I'm going to give you a grammar, and then we would find out what language this grammar is representing. That's a very good practice. Let's start with this simple example. So S is defined as A, S, or lambda. The question is what language this is representing, and we denote this concept with L of G. So we are looking for L, or the language of this grammar. All right. Here I am trying to find out what strings can be derived with this grammar. So let me, for just this one, I separate them. So S goes to lambda. Okay. So definitely we can say S derives lambda. So the first thing that this language contains is the lambda. What else? S derived, let's start with this guy. It will be A, S, and this S can be substituted with lambda, which gives us A. So the next one is A. And what else? This S could be substituted with another AS, and this S could be substituted with lambda. Then it would give us AA. And you know and you see where we are going, right? This grammar is defining what? Any number of A's. So what is the set builder for that? Oh, we are so familiar with this. N greater than or equal to 0. So this is the language. Okay, so the better way is this way. L of G is equal to A to the N such that N greater than or equal to 0. Okay, now the question is, if I change this grammar instead of AS or lambda as SA or lambda, any difference? I mean, this grammar, what language this grammar is going to produce? Does it generate the same language? Yeah, the same thing. So again, we would say S derives the lambda. So if this is the language, so the first guy is lambda, and S can define SA, and we can substitute this S with lambda and we get A. We can substitute this S with another SA and then substitute this S with lambda, we get AA. And yeah, you see the same thing. For this particular example, there is no difference between AS or SA. Another example. This one, S, is defined as A, S, B, or lambda. The question is, what is the L of G? Okay, let me have some imagination what strings it can produce. So definitely the first one will be lambda, like we explained in the previous slide. And what else? So S can derive A S B. And you agree that this S can be substituted with lambda, we get AB. So AB can be produced here, or we can substitute this S with another ASB. So it will be ASB, B. So in fact, this guy is the substitution of this S by using this production rule. All right. So, and if we substitute S with the lambda, we will get A, B, B. And I am sure that you guessed what language this grammar is producing. This is our famous language. Is L of G is equal to A to the N, B to the N, such that n greater than or equal to 0. As you see, the number of a's and the number of b's always is the same. Because when we substitute this s with another ASB, we add one a on the left and one b on the right. So always the number of a's and b's are equivalent. Fantastic. So we need to keep in our mind these languages. Okay, so can I have a conclusion here? Because I just somehow proved that this grammar is representing A to the N, B to the N, which is a non-regular language. So grammar can represent non-regular language. And in the previous example, it could represent A to the N, which is a regular language. So can I conclude that grammars not only they can represent regular languages like this, but also they can represent non-regular languages as well. So far we can conclude that hey, grammars are more powerful tool than regexes because regexes just could represent regular languages. Very cool conclusion so far. Okay, another example. S goes to A, B, but A and B are defined as A lambda, B lambda. Oh my God, we are familiar with this too in the previous examples. So this guy is equivalent to any number of A's. Yeah, and this guy is equivalent to any number of b's. In the previous examples, we had as. Yeah, s is defined as this or lambda. So if you compare this with this guy, just the s is changed. But we can conclude here that, hey, this is any number of a's. And this is very similar to that one. And yeah, just consider these as the dummy variables, right? So these sub-rules, they produce any number of b's. And if we substitute any number of a here, any number of b here, what do we get? Yeah, I am sure that you just guess what's happening here. So it will be a to the n, any number of a's, b to the m, any number of b's. Not necessarily these two can be equivalent, right? So that's why we use different variables for that. A to the n, b to the m, such that what? N can be 0, yes, because number of a's can be lambda, so greater than or equal to 0, and the same thing for the m. Fantastic. So this grammar representing this language. And we used our knowledge from the previous examples. We are still sharpening our knowledge and skill, but in this section, we have different experience. Now we give you a language and we ask you to produce the grammar. Yeah, let's have some examples here. Find a grammar that generates the following language over A and B. W is defined as W belongs to sigma star. This is all strings. We need to produce all strings. This is not something that we can give you a simple way how to think about that. Every language, we need to go back and forth and try to design a grammar for that. For this simple one, we need to have a production rule or some production rules that we can produce any number of A's and B's. So any combination of A's and B's after some thinking and brainstorming, I would say, okay, so I need any number of A's can be combined with any number of B's. So this S can be substitute with also B as well. So if we have this and also I would need lambda as well to terminate, the final termination. Because if you don't have this lambda, these s's cannot be replaced with something. Yeah. And this lambda is actually the final termination of those recursion. All right. Look at this and see whether we can produce any number of A's or any number of B's or any combinations of A's and B's. So I would say ASBS, right? Okay, so let me see. If I want to produce, for example, this BAA. So since we are starting with B, I would go with this production rule and I would say, all right, S defined as BS. Now I need an A, so I substitute this S with this guy. So I would say BAS. So this AS is a substitution for this S, right? Since I need another A, then I would say this BA and substitute this S with another AS. And finally, BAA lambda, I substitute this with lambda, and this is equivalent to BAA. You see, is this the case that this grammar produces this language? Yeah, as long as we cannot break it, and as long as we cannot take an counterexample, we would say yes. So we can combine this as the convention that we learned. So S goes to or is defined as AS or BS or lambda. So this will be the solution for this language. Of course, this is not the only way that we can solve this problem. I am sure that after some brainstorming, you can come up with other solutions as well. Another example, W contains exactly one A. Fantastic. Exactly one A. Yeah, we have seen this language before. Exactly one A. It means that we have one A here, and before that and after that, we can have any number of B's. Yeah, you remember this was the regular expression for this language, right? When you look at this pattern, what do you get here? Yeah, I can say this is S is defined. Let's call it B here. And we have A here and another B here. So any number of B's, I substitute as a B here and any number of B's here, another B. So how can we define this B? Any number of B's? We have seen this before in the previous examples. So B can be defined as B, B, or lambda. All right. Okay, so here I put some exercises for you guys, and I'm gonna stop here. See you guys in the next video.